Okay, welcome back everybody. We're on part 2 of the Phase Linear 4000. First of all, I'm going to take these 3 things with all the controls, and I'm going to put them in the ultrasonic cleaner. Now today what I'm going to work on is, as some of you have and I did get some really good advice from some of you viewers. I want to mention those right now. First of all, these connectors are notorious for failing. What happens is there's a lot of force that gets put on them by the circuit boards and they crack. Now it looks good on the surface, but as you get closer and closer, I don't know if you can see this, but for instance right in here, there's cracks already in there. And what will happen is you'll get these little rings, little crack rings around there, and the pins won't make good contact. All of the connectors, these are just terrible connectors. They break very easily, they're very brittle, and there's no other alternative but to put new old stock or put this same type in there. Now and it's because of these silly little grounding switches that are in there. And the whole purpose of the grounding switch is to ground out the inputs so you don't get noise, I believe. And of course you can just see how flimsy they are. They're going to wear out. So if we start with brand new ones, at least we know that for the foreseeable future it'll work. Now you probably could find some sort of a panel mount jack that would fit in there, but that would be kind of hard. Looking at how closely spaced they are and how close they are to the board, it would be hard to put something, with a nut on the front of it with these size of holes that has a switch in it. You could probably do without the switches, but I don't know what kind of consequences that would give us. So I'm going to use, like I said, I ordered some new old stock that were available online, and hopefully that'll fix it. Okay, first things first, I'm just going to flow a little bit of fresh solder on here because this old crusty stuff sometimes can be hard to heat up with the desoldering tool. So I'm just going to go and do this first. So let's see if this thing will work now. And I don't know if this tip's still big enough to get over top of there. Yeah, I guess it is. Yeah, much easier this way. Like I said, if this is too noisy for you, I totally get it. You can skip through this part. Matter of fact, I might skip through this part and come back here in a minute, because I can't really do much soldering and chatting when I'm doing this, especially with all this noise. So let me finish this and I'll come right back. You get the point of what I'm doing. Alright, that's done. Let's see how these come off now. They still can get stuck. And I only lost one solder pad, which isn't too bad. I can see a couple spaces where these are still stuck a little bit. These are hard to get out. Now I've noticed that some of these use the actual grounding pin and some of them do not. Like this one here that lost its little pad, which I'll take off for the moment and put it aside. It isn't connected to anything. Like some of these are not, some of them are. So I guess if you could like shuffle these around if you had one with a bad switch in it. See, that little switch is just, the whole idea is when it pushes in, it like comes off of there, see? Comes off of the ground. So it's like a shorting pin. I mean, I get what they were trying to do, but just, they probably could have used a better product than these. And you can see as I'm taking them apart, they're just, things are just falling out because of just that cheap plastic on there. I think I'll just use some brush on flux because it'll be a little easier to deal with. So let's see. Use this brush? I'll just use this brush. I can clean it off. No big deal. And then we can just go over it with the alcohol and clean it. But this will ensure that we get a good connection. Alright, let's see how this goes. Just start on one end and work my way over. Try not to get this all over me now. You can't, the other thing I learned from this is you cannot go too crazy with the dwell time. You don't want to leave it on here for too long, because what happens is the little plastic carriage that these pins are held in, the little plastic housing or whatever, it melts. And then the pins go crooked, and then they don't stay straight in the connector. So you have to kind of get on and get off. You have to have a good iron with good thermal mass and thermal recovery. If you get ahead of your iron, you're better off waiting a little bit and let it recover the heat, so you don't have to stay on there for so long. Okay, you want to wear gloves when you do this, because alcohol mixed with flux is just nasty on your fingers. You can't get it off. It stinks. Your fingers will stink for the next day. So be sure to glove up if you're going to do this. And again, you're going to have to do this several times to get all this stuff out. But when you're done, it's going to look pretty good. All right. So I'm going to let this all dry and see what it looks like. If it looks good, we're going to let it go. And if not, we'll just keep cleaning it till it's clean. Okay, so we got the board all cleaned up. It looks a lot better now. And really, there's only a few components on here. Some diodes, transistors, and this Viagra transistor. Yeah, you just can't unsee that, can you? You know what? I'm turning this thing into a eunuch. I can't stand it. There. Better. Okay. So, few capacitors. These are just power supply ones. I'll go ahead and replace those real quick. I'll clean up the leads on these diodes. I'm sure they're fine. We'll test them very quickly, but I think they're fine. And I think we'll be good to go. By the way, if any of you watch Shango 066, he did a restoration of an old tube radio from a Philco radio from the 1930s, and one of the alignment tools they called out was the fiber alignment tool, I think it's called, and it has a part number. This is what they're talking about. This is a remake of one, a modern one. The original ones were fiber the whole way across. These have little nylon. Really all this is a nylon bolt on each end. And what this is for is when you're doing the alignment of the IF stages on the old Philco radios, they're very sensitive to any kind of electromagnetic coupling, like to your hand or the tools or anything. So you can't have any metal tools. You can't get close to it. It really throws things off, and that's why they use this. So basically, you use this and kind of hold back here, and you can adjust the IF, those little trimmer capacitors, without shorting them out and without coupling yourself to them and throwing off the alignment as you're trying to set it up. So that's what this is. You can buy these, I think, on eBay. Every now and then they'll have a seller that sells them. You look it up and you'll see this, and they're not real expensive, but you can pick one up. Or you can make one yourself from just a piece of plastic rod and or fiber board rod, whatever, and then I think this is a 1/4-inch bolt, and they drill a hole down through the middle of it for the little screw of the capacitor to go through. But that's what this is. So not only do they glue these capacitors to the board with this silicone RTV crap, they also fold the legs over and then put a big blob of solder on top of it. So yeah, they just make it fun the whole way. I told you at the beginning of this series that this was going to be another fun and frolic project. Sure enough. Alright, we have recapacified this board, and you know, now that I think of it, probably before I turned this thing from a rooster into a hen, I should have checked to see if that leg sticking up there was actually a test point, but I guess it's too late now. There's still a tab there I can get on there with a meter, so I should be good, but we'll see. Everything else on this board's done. This was the easy one. Now we get to the fun stuff. So looking at this board, this was the one with the toothpicks, and it appears as though someone has tried to reflow these pins at some time but didn't do a very good job. And there's a lot of them that are cracked. So we're going to go clean that up. I don't know if this is a trace that got torn off or if this is a modification somebody made here. I'm gonna have to look. There are a few mod notes I have for these. I want to see why this is in there and find out what this is, or if they're trying to jumper something out. It would be interesting to know what they're doing here. Okay, so this is a later version of the board, because if you look at the early version, this is C17 capacitor right here. And you can see on here, there is no C17. But on a later print, there it is right there. You can kind of see it. And according to this, they are supposed to be joined together right there. I don't know if you can see that, but right over here. So that is correct. Okay, maybe I'm just not as technically advanced as phase linear, so I just don't understand the technology here. But correct me if I'm wrong. This is a regular potentiometer. It's the same as, you know, any other potentiometer. However, comma, it has this detent thing on it. Now, we know how these things vary, you know, from one pot to another. So does this mean that this is their idea of a stepped attenuator? And what happens if this resistive element is not properly lined up with this one? I mean, would you adjust the bass and treble controls differently then? Because I mean, we all know that these pots are just a little bit different in their positions, you know, from one to the next. I don't really understand why they did that. I mean, wouldn't it, every other stereo out there, just they have a pot connected to the knob, you know? So was this an attempt to make you think you're getting a stepped attenuator when in fact you're not? Or was there some kind of advantage to this where they're thinking maybe the steps will be, you know, equal amounts from the two sides or something? I don't know. That is so bizarre. We're being phase lineared again. I did clean up all these reflowed these joints here so that they are a little bit better, but yeah, I don't know. Next thing I'm going to work on is this peak unlimiter board, and all I'm going to do is replace all the electrolytics on it. It works, I'm pretty sure, and there's no adjustments on it, so there's not much to do other than recap it. Okay, so after taking a quick dip in the ultrasonic cleaner, these two boards are much better. Look how well these things turned out. I mean, they look new. And it all is, You know, when you looked at all that flux and all that crud and everything, all the controls are perfect now. And what I'm using is a product by Alkanox called Detergent 8. It's pretty expensive stuff, but a gallon of it lasts years because you only use a little bit in your tank of ultrasonic cleaners. And you want to also use deionized water. Not ionized water, that's the drinking kind of stuff you see in a grocery store, but deionized water. You can order it a lot of places, and you mix it with this Detergent 8, and this does just look at this, how it was, you know, from how it was just covered, if you remember, just coated with gunk. So anyway, we're over to the peak unlimiter downward expander board. This is a really interesting circuit. So before we go any further, I'm going to replace all these capacitors, but these black ones here are in pairs. And they're pretty critical to the function of the circuit, so they have to be matched. And I'll show you a little clip of that here in a minute. But let's look real quick at how this circuit works, because it's interesting. So any of you people that like circuit chasing electrons around, this ought to be a little bit of fun. Now this took me a while to figure this out because it's not really apparent at first what this thing is doing. And really what it's doing is you have three different ways that you're going to affect the signal, you know, your audio signal. You're going to increase the gain, you know, very quickly. This is in a very short time frame of any peak transient in the audio. So somebody kicks the kick drum or hits a hard snare drum. That's normally a very overpowering, overbearing sound. And it tends to get compressed quite a bit when they're encoded into your vinyl record or tape or whatever, so that it doesn't distort. You don't want clipping to happen. And what this is supposed to do is bring it more to its natural sound, how it would have been when it was live music, without clipping. So it's increasing the gain of that peak to kind of expand the dynamic range while still limiting it from overdriving into distortion. So that's what the peak unlimiter does. You then have another thing called the downward expander. I don't know where they came up with that name, but essentially what it is when there are low passages of music, sometimes those low passages will get kind of mixed in with the noise floor, and they'll kind of sound flat. They won't be as clear. So what you want to do in that instance is, in those areas where you have a real low passage, you want to boost it ever so slightly to bring it up out of the noise floor without it actually sounding louder than it should have when it was live. So that's what those two things do. And then there's this third circuit called the linear expander. And the linear expander just kind of samples the overall signal, and then it will kind of control the amount that these two effects are going to have on the overall signal. And we'll get into that here in a minute, but that's what these things are here. So if you look, you have a threshold level coming in. So there's another couple of transistors, and it's just sampling both the left and right channel audio and making pretty much a voltage controlled circuit. I'm not going to call it a DC voltage control because you could see this capacitor decoupling here, but essentially it's going to put a sample of both channels together into here. So and then this is going to sense that peak level coming from the two channels combined. And that's what's going to kind of give you the threshold of how much this operates. And there's actually a threshold knob on the front of the preamp that lets you set that. So you can set how much you want this effect to integrate into the original signal. So that's what that does. And the main reason that there's two different circuits here is because of the time constant in which they're working. Now when we're looking at the peak unlimiter, this time constant on here is going to be, it's going to give it a fast attack and a slow decay. What does that mean? It means that very rapidly, because of course a kick drum or a snare drum or something like that hits really quickly and then goes away. So you want it to react very quickly. So any of these real high level signals like that, they're going to trigger this circuit very quickly. And that's all done by this timing circuit in here. It's all analog through capacitors, RC time constants. And that's what's going to release this signal. And again, it only works with high level, high level dynamic signals. And then that's going to put out a voltage that's proportionate to the amount of unlimiting you want to give it. And that feeds through A and A prime, which they're opposite. And I'll show you why these are one's in the inverse of the other here in a second. And you can see it feeds up into this first circuit up here. We'll just look at, there's two identical circuits, left and right channel, but they both work the same. But they're both controlled by the same peak unlimiter and downward expander circuit. So you can see those two signals come in there, and one of them is going to be in phase. The other one is going to be inverted, 180 degrees out of phase. And that's why you need that inverted signal, because what this is doing is this is your envelope detect. What it's looking at is any positive going signal versus any negative going signal. So once again, you can see how these capacitors have to match one another, or these signals will react differently to one another with respect to positive half cycle and negative half cycle. And that would sound terrible if they were not balanced, if they were not time coordinated. So, and then I would even argue that these diodes should all be matched as far as forward voltage drop and so forth. I don't know if they are. Maybe they were. I don't know. I'm not going to touch them if they work. I'll tell you that. So then your envelope detect signal will go in here, and it goes into another comparator. And you also have your left channel input. So this is the actual audio input coming in here. And you can see this is the inverting input of this comparator here. So what's happening is this signal is controlling the amount of gain of this signal. So what's going to happen is if that peak unlimiter sees a big peak coming in from our threshold sensor, it's going to activate, and it's going to increase the signal here, which is going to increase the gain to this signal and allow that peak transient to come out the way it was intended to be, of course, or so we think. Conversely, with the downward expander, during a quiet passage, it actually has a more slow attack and a slow decay once again. And the reason they both have a slow decay is you don't want this thing to have that breathing effect, because it will make the sound get, louder and softer, and it'll really be an annoying effect. So anyway, this one's going to take a little bit longer before it'll kick in. In other words, you have to have a longer period of time of low signal strength, of a low signal level, before this will kick in and it will activate. When it activates, it goes into this signal here after the peak expander. And again, it's going to control the amount of gain at the lower levels. So if it sees that the signal is below a certain threshold, it's going to boost that signal a little bit to get it above the noise and to make it a little clearer to hear. And again, that's going to take a little bit longer. So it's going to kind of fade in as the as its low signal level for a long period of time. Last but not least, that feeds into this final op amp here. So you have these two op amps that kind of work together, and you have your linear expander circuit driving this. And again, this drives the gain of this op amp. So, and I called this a comparator, didn't I? Oh well. You should be used to that by now on my channel. So anyway, this op amp's gain will change, again, based upon the linear expander. And the linear expander is really about how loud or how soft is the music itself. If it's a loud recording to begin with, that was recorded at a high recording level, it's going to throttle this whole circuit down a little bit. And if it's a very quiet record or recording or whatever, it's going to allow this to have a little bit more gain. And it'll throttle it up a little bit. So those three circuits work together, and again, if it does it quickly enough and subtly enough, it should give you more dynamic range. And so everything should sound more live. And if you've ever heard music with very high dynamic range, like some digital music today on certain systems, there is a difference between how that sounds and how some of the old analog recordings sound that are limited by the media. Tape emulsion and record grooves and so forth, they just have a maximum signal strength before they start to distort. It's just a physical characteristic of the media, and it's a lot lower than what you can get with digital media. So they had to do things when they recorded this stuff to make it work within those parameters or in those limits, which some would argue it limits the dynamic range of the music and it doesn't sound as good as it should. Again, I think sometimes people like the analog because of that. It sounds a little bit more reserved, a little clearer. Other people like that real powerful dynamic sound. Just depends on who you are and what you like. But this was obviously some sort of a attempt at getting an analog recording to sound with the same kind of dynamic range that we now take for granted with digital. Hope that makes sense. So that's what this is. And you can see anywhere you have these diode networks like this, you're looking at the positive half cycle and negative half cycle. And this capacitor in with this resistor is a time constant. And as a result, if these don't match perfectly, it will affect the time constant. It will have a different effect on the positive half going cycle than it will on the negative half. So again, that's why all these ones have to be matched. And that's why I'm going to just use these film capacitors that are plus or minus 5%. Electrolytic caps, they had to be matched back in the day because a lot of them were minus 10%, plus 20%. So there's a big range that those could operate in. And these, not so much. They pretty much hold solid throughout the audio spectrum, frequency spectrum, and they're accurate. Like I said, 5%. That'll be more than enough. It'll take care of this. So that's what we're going to do. We're going to replace these capacitors with these capacitors. Okay, peak unlimiter board is all done. And it is another day. Hopefully I will finish this project this weekend because I really have other things I need to get done. So I replaced it with all film capacitors, all the 0.1s and all the 1 microfarad and 2.2. And I just realized I forgot one cap here. I'll have to swap that out. Anyway, we're done with that. The next thing I want to do is look at the correlator board and see if there's anything we really need to replace on it. If all these capacitors are good, I am inclined to leave them alone because I don't really think this thing, I don't want to put any more time or effort or money into it than I have to, because I don't know how much this thing would sell for. I'm not going to keep it. I don't believe Dave is going to keep it. He probably, if he doesn't already have an example of one of these in his collection, he's probably got something similar. So this will get sold, and again, I don't want to put big time into it because I have other things I want to get done. So let's look at the autocorrelator circuit and see how that works. So first of all, what is an autocorrelator? Boy, you got to love all these terms. Basically, it's another type of noise reduction. And it's a single pass noise reduction. So in other words, it reduces the noise on the fly, as the signal passes through it. Whereas when you use like an encoding based noise reduction like Dolby, you actually have to put a Dolby preemphasis on there. Like you encode it with Dolby, and then when you play it back, you decode it. So it's kind of a two-pass system. So if you didn't record the material with the Dolby, then using Dolby to play it back won't work properly. Whereas this is designed to work without any type of encoding or anything, if that makes sense. So here's generally how this thing works. You have your left and right channel coming in, and they go straight to the left and right correlator boards, which is this. More about these in a second. They split off and go into this summing amplifier. And all this thing does is it combines the two channels, so all the frequencies and amplitudes of both channels combined come out as one composite signal. So we'll call this a composite signal. It then goes through a logarithmic amplifier. This log board, which is this board right here, it takes, and you can see there's a correlation threshold setting. Actually, I think this is the low frequency. I can't remember. One of these is this, and the other one is on the front panel of the unit. And what this does is it amplifies the signal logarithmically anything above 2 kilohertz. So you have one output of anything 2 kilohertz and above. You have another output that is just direct amplified by the log amp that's anything below 200 hertz. So it's splitting these off because hiss and so forth is in the high frequency spectrum, whereas rumble, like you would see in a turntable, is in the low frequency spectrum. It's treating these as two different things. You can see this one here, actually, the threshold of where this thing triggers is set by the frequencies above 2 kilohertz. That then goes through two bandpass filter boards. So you have bandpass 1, and this has two sharp filters on it. One of them is centered on 4 kilohertz. The other one is centered on 7 kilohertz. And the purpose of this is it's taking those two signal ranges, or those two frequency ranges, and it's creating a gain level. So there's a voltage output that represents the amount of gain you want in those ranges. That's what this is doing, as far as I understand. Some of you Carver people might be better at this than me. Then the next thing you have is a bandpass 2, and this is kind of cool because what this is doing is this, again, has a 200 hertz low pass filter on it, and it has a 12 kilohertz high pass filter. And what it's doing is, once again, it's using those two frequency ranges to determine what gain levels to apply or to reduce, whatever, to the low frequencies and the high frequencies. So the low frequency, it's trying to remove rumble, and the high frequency, it's trying to remove hiss. And what this is doing is kind of cool because it's looking at the harmonics of the original signal, and then it's creating a filter based on the harmonics, because of course the actual audio is going to be louder than the noise. So your hiss and everything is going to be at a lower level. So what this is doing is it's trying to pick out, and these are kind of like little bits, digital bits. They're not digital, but by turning on, if you go over here, you have these correlator switches, they call them, and you have these little switching diodes, and each one of these is like a bit. And by turning these different combinations on, you can set these you can make this really complex set of notch filters that will allow the audio to pass through, but anything that's not the audio, which would be like the hum or the rumble, would be blocked, would be filtered by these sharp filters. So it's kind of cool how they're doing it. And it's doing this in real time very quickly as the music is playing. And that's what this does, is this splits that off, and then they apply the gain level to the bandpass filter. So when this comes in here, you have two pieces of data. You have data that is all of the frequencies that you want to allow the unit to pass through these correlators. And then you have the gain level that you want to apply to those frequencies, so it can actually throttle down or up. And then it goes from there into each correlator board. And with that information, it really doesn't care whether it's the left or right channel. It'll apply it to both of them equally, but any of the noise that would be in either place, the actual signal would pass through because of these bit filters, but any of the noise would be filtered out. And this is all happening real time. So you can see how complicated this is. And I think about whether this is a good idea or not, whether it works really well or not, whether you like the sound of it or not. I'm very fascinated with the whole theory of how they're doing this. You got to realize this was all done, with total, analog circuitry. And it's fascinating. Now we have digital signal processing and things. If you've ever had a DSP receiver, you hear how quiet they are compared to some of the old analog receivers out there. It's pretty amazing, but that's all done with lots and lots of computing power. This is done with just analog filters. So it's pretty cool. And that's essentially what's going on with this thing, and that's what these boards do. And again, going back to this, these little emitter follower circuits, all these are is impedance matching emitter followers. The actual filtration is taking place through these capacitor and resistor networks. You can see once again you have these capacitors, 1 microfarad, 0.22, 2.2. So like these ones here these all have to be matched once again. So really, these two caps here and these two caps here, since they're electrolytics, I may replace those ones. The rest of these, as long as they can, pass the signal, I'm not really worried about it. These ones are film already, the 0.22 and the 0.22 here. So, that said, I'm only going to go on these correlators, and I'm going to take these, what is this? This one, yeah, there should be two 2.2s. Okay, here's a naked 2.2. Where's my other correlator board? And this one has, okay, here they are here. As you can see, you have your two, yeah, I guess this one's the same too. I don't know why they have one that looks one way and one that looks the other. It's kind of strange. I think they just kind of used whatever caps they had. So you see these are a little different. These ones don't match these ones. I don't know. But I'll go ahead and I'll replace these 4 here. And I'm going to leave these other ones that don't really matter for what we're doing. And yeah, we'll put it all together and this thing should be ready to test. Of course, looking at the ESR, that one's about 5 ohms. That one's about 4.5 ohms. That one's about 5.5 ohms. And that one's about 5 ohms. So they're all different ESR. That's not good. And then looking at these 1 microfarads, these ones are even worse. 7 ohms. And that's 6 ohms. And then this one is 2 ohms and 2 ohms. Going down the list here with the rest of them, 3. That one's shot. That one's shot. Yeah, these caps are all bad. So, guess what? Wow. We need to do a recap on this. It's strange because the peak unlimiter board, those caps weren't that bad, but obviously this one did not hold up as well. So let me get those swapped. Okay, so I have one of the boards done. I'm going to move over to the other one, and I noticed like just things like this. You see how these little capacitors are kind of down, you know, close to the board, and then you look at these, they're like sticking way up in the air, just waiting to short out on something. And like I said, they use different caps on either. I mean, maybe these were made at different times and then put into the same unit. I don't know. But I don't know if you could look at the Rev Gs. But yeah, the build quality on these things is wow. I see why you read a lot of negative things about this kind of equipment online. I mean, I'm kind of wanted to look at it from my own perspective, but I'm kind of starting to see people's point. Anyway, let me get this board rebuilt. Okay, I put it back together, and yes, I ended up recapping all of the boards because the capacitors were all over the place with ESR. And yeah, this is a capacitor changer's wet dream right here. Look at all that. If you like recapping things and that's a relaxing thing to you, I would suggest picking one of these up. There, you can sometimes find them cheap, and there's lots of capacitors for you to replace. So anyway, it's all put back together now. You can see, I'll show you the boards here a little bit. You can look down at them. So here's your two correlator boards, your filter board, or your bandpass, and your other bandpass, and your one of these is the encoder, and your RIAA is over here to the right. Right here is the RIAA board, you know, for phono. The logic board, the tone amp is here. So that's pretty much everything there. They're all plugged in. They just kind of plug in there. And as you can see, I was able to adjust the controls, the shafts and all that, so that this is now plugged in the whole way. So we don't need to reinstall these, which is a good thing. All right, now here's the thing. I turned it on and it works, but there is one problem. Let me show it to you. So I'll turn it on, have it set to 2-channel, all that good stuff, have the volume down, and I'm using the DG4162. I just have a 1 kilohertz signal going into both channels equally, and if we look at the scope, I have both channel 1 and channel 2 superimposed over one another, and if I turn the volume up, it looks pretty good right now, right? Let me zoom you in. See that? But watch as I keep going up in volume. See how they separate? Now the channels are not the same amplitude with one another. And then as I go up further, it closes back up. And they're pretty close to being on top of one another again. Not quite, but close. As I go down in volume, right in that middle volume level, you could see how grossly off they are from one another. See that? So the left channel is way weaker than the right. So the next thing I did was I disconnected the output of the preamp, and I hooked a set of probes up, and I'll show you. So you can see now I have the oscilloscope probes connected, and where I connected it was right onto the potentiometer, the volume pot, the input of the volume pot, and I'll show you where that is. So you can see we come out of the correlator. So you have the inputs, you go through all this mess here, through the tone control, through the correlators, and then you get to your volume pot. So you have your input of the volume pot on this side and this side. So for your right and left channel volume, and you notice they're tied together. And so that'll be the full signal unattenuated by the volume pot. And if you look, there it is. And you look there, they're perfectly overlapped. Absolutely perfect. Now, what I'm going to do is I'm going to move the probe from right up here to the actual wiper of the pot. So from going up here, we're now going to test here. And then we can watch as we turn the volume up and down on both channels. Let me do that. Okay, you can see we're now connected with both probes on the center wiper of the pot. I have the volume turned all the way down. And as we turn the volume up, you can see they already start separating. Then as you go up in volume, they go back together. And I have to make this a little more sensitive so you can see it. So now that's volume all the way up. And then going down, you see how they drop out of sync? And around middle volume, it gets really bad. See that? And then they go back together just before you turn them all the way down. See that? Now, that thick line is because I have a 10 times probe and I'm only on 20 millivolts per division. But it gives you an idea. You can see how far out that is. So what that tells me is these are cheap carbon potentiometers. And what it's telling me is the carbon traces on the carbon tracks on the pots are not matched between the left and right volume pot. And that's a pretty significant difference on this one. Most of them will be off by a wee little bit on this type with these types of pots, but this one is significantly out. And I don't think I'm going to be able to adjust it any, to bring it in. It's just that far off. So unfortunately, the volume is not going to be correct. And again, it's not the balance control. I can turn the balance control to balance it out, but this is actually before the balance control. So if I go back down to the schematic and I show you, the difference is right here. So we're seeing it in the pot itself. But then it goes through the peak unlimiter board, and it'll bypass it if you're not using it. So we're in bypass mode, so it just goes straight over here, comes down these two wires into the decoder board, and right here is the joystick for the for right and left, front and back. And if you notice, if you turn this, it's right now showing you in 4-channel mode. If you slide these 4 sliders up into 2-channel mode, it grounds out the rear channels and only plays the front channels. And of course, these pots will allow you to balance it. But the problem is when you turn that balance pot, by the time they're balanced, that balance pot is turned all the way to the left, or 2/3 of the way to the left, just because of that difference going in there. So it's not a balance pot problem. It's the actual volume pot that's bad. So I'm not sure what we're going to do about that. I mean, you can't really live with that because it's a significant enough difference that you would hear it. One channel would sound louder than the other, especially as you turn the volume in that mid-range, because I'm right here. You can see right there's the dot. It's just around halfway. And then it's not until I get all the way to about here that they join back together. And on this side, it's not till I'm about here where they join back together. So at the low volumes, it's close. Mid volume range, it's way off. So, yeah. Okay, so a couple of need to know things here. Number one, this is just a standard pot. I think it's not even a logarithmic taper. I think it's just a linear taper pot. And what they did was they put this 56K, or this 56 ohm resistor, you can see on each one, at the end of the pot, at the low side of the pot. And then they came over here and from the wiper to ground, they put a 39K potentiometer or resistor. And you can see those 4 resistors down here on the little volume pot board. And what that is kind of a poor man's logarithmic taper pot. Now, these two pots, these two elements are tied together mechanically, and you can see that. There's a front one and a rear one. And what you can do is you can take a small screwdriver, and there's a little notch in there. Let's see here. See the notch? Right there's the notch. You can kind of see it go past. And you can hold this in, and you can kind of force turn it, and this element will turn while this one stays still. And this will slide on there to allow you to align those. The problem is it's not the alignment that's off. So if you look, I was able to play around with it a little bit, but what happens is when I'm here at one end, it says 5K. And now this is going to go up and then back down. It's going to read funny because of the way that logarithmic thing is. But essentially, as you turn this down, you can see they already go out of sync. And if you synchronize them there, they'll be out somewhere else. So really, the actual taper of each pot element is different. Bad pot. See how this one's at 225K, this one's at 150K, and that's just because of that. So they're bad. So we tried. I mean, at least I showed you how to work on one of these, but you can see they're both grossly off. They're only supposed to be 100K each one. So you can see 100K pot and 100K pot. Right there, 100K, 100K. And I got 150K and 224K. So garbage. Garbage. So in light of finding this to be bad, there's a couple of alternatives. I can try to find another one of these originals, which these are not going to be easy to find. Or I can replace it with something different, more modern, which is just what I've done here, and I'll show you in a second. But what I put in there was one of these. And you can see it's 100K. It's stereo. And I don't know where I got this. This might have been like an eBay or a Amazon purchase. But what it is it's not a potentiometer. It's actually a dual-stepped attenuator. So inside here, these two circuit boards have a whole bunch of little absolutely minuscule tiny resistors, surface mount resistors, and then a switch contact that goes around there. And they're all in series, and the values of the resistors all add up in series to 100,000 ohms. So from here to here will be 100K. We can see that very easily using our meter. And there it is, 100K. Roughly. Depends on the accuracy of each resistor as well. And see, they're both the same. Now, what this does is each resistor is additive, so as you rotate this, see how it clicks? Each position picks off another section of resistor until when you go all the way from one end to the other, it'll select all of the resistors or none of the resistors or something in between. So that's what a stepped attenuator is. Now when you play around with the value, so if you made, say you have 20 steps in here, and you had each step was exactly 1/20th of 100K, which would be what, 5K? Then you would have what's called a linear taper pot, meaning it moves linearly. You know, each step is the same amount. If you make the resistors a smaller value on one end and a larger value on the other, then you'll have what's called a tapered potentiometer. And if you make those a logarithmic increase of resistance as you go around, that's called a logarithmic taper, and that's what this one is. So that is a very common type of taper because it matches the human ear. So it's increasing the volume slightly in the beginning, and then as you go further around, each step gets more dramatic. So it kind of makes the volume control sound as you rotate it. The sound will increase in a smooth manner to your ear, even though you're changing that resistance in a logarithmic pattern. So anyway, this is a drop-in replacement for this. But if you remember on the schematic, this is a linear taper pot. And what they did to make it logarithmic was well, let's get the schematic real quick. So as I showed you before, they're just taking this 100K pot And then from the wiper to the one end, they're putting a 39K resistor. And then they're, at the end of this one, they're putting a 56 ohm resistor. And this is kind of going to be a poor man's logarithmic taper. Whereas, so we don't want that influence on this because this one already has the logarithmic taper baked into it. So what I have to do is I'm just going to simply remove these two 39K resistors. Now, it doesn't hurt to leave the 56 ohm resistor. That's not going to hurt anything. I don't think they want you to hard ground this input of this tone amp straight to ground, so they want it to be lifted ever so slightly above ground where it will make the volume sound, you know, completely down, but still not put a total ground from here to here for whatever reason. So I'm going to leave that one, remove these 39Ks, and then just put that logarithmic pot there. And I'm sure someone's going to say they want to see the logarithmic taper, so I have the meter connected. It's turned all the way down right now, and you can see that's your maximum resistance. And then if I go each click, so the first click hardly moves it, right? The next click, see, it's just moving it a tiny little bit. Now I moved it a little more that time, right? Here's the next one. We're still, now it dropped below 101K. Now you're going to see each one of these ones is going to get a little bit more. See that? And eventually, you're going to see it make some pretty dramatic changes. See there? Each one's getting a lot bigger change as we get close to the, look at that. And that's it. So that's how that works. So that's a logarithmic taper. Okay, so here is that pot installed in there. And I just wired it in. And then those two 39K resistors that used to be here, I've removed them, but I left the 56 ohm resistors in. And that's it. Okay, before we get to any music, what I want to do is I want to check the tone controls and make sure they work. Because remember, the potentiometers were bad for the volume. I want to make sure the tone ones are tracking properly. So let's take a look and see. There we go. So all we're going to do is I'm going to turn the tone control from flat to on or in, whatever you want to call it. And then these are your turnovers. So you have 8 kilohertz and 2 kilohertz for the high frequency for the treble control. And we have 40 hertz and 150 hertz for the bass control. And then you have a separate bass and treble for each channel. And again, I have everything else is just in bypass. I don't have any effects or any of that stuff on right now. So let's get on the scope. And I have it, right now I have the control set to flat. And you can see it is pretty flat. I got a pretty flat response there. And I'm looking at a square wave because the square wave is going to kind of show the action of the bass and treble control. So now I'm going to turn the controls on. And you can see I have bass and treble are all set to flat right now, but take a look. They're not flat. So, for instance, I'll take the right channel bass control, and you can see how that kind of messes with it a little bit. And I have it almost all the way down. I'm 2 clicks away from all the way down, and that's about as flat as it gets. And then the right channel is completely different. See that? That one will flatten out, but I have the bass turned all the way up right now. So you can see those controls are not working really well. Now there's the treble on the right channel. And there's treble on the left channel. Now let's look at I'm going to go change the turnover on both of them. So here's treble turnover, bass turnover. So I changed them now to 2 kilohertz and 180 hertz, or 150 hertz, I'm sorry. So here's right channel bass. You can see right now they don't match. They don't match at all. So on the right channel, there's your bass control, and that's pretty much doing what it's supposed to. The treble control, however, right there is flat, and I'm actually one click to the left. Remember how I told you these have these little detent things that are attached to the pots? There's your problem. And I have a feeling that this potentiometer has the wrong, it has gone high in value. And if I go up, now on the left channel, that one's working properly. See that? And there it is set to the flat position. It's pretty flat. So this one should really be about here, and it isn't. So it tells me these pots here are probably a little bit out to lunch too with their adjustments, but I'm not going to replace those. How much time and money do I want to put into this thing? So the other thing I noticed is when I put these on the 8 kilohertz and the 40 hertz, it's not flat. That left channel again is, see how it's just kind of not flat. So that could be partially the treble pot has gone high in resistance, and it also could have something to do with the capacitors, which I thought I replaced all those in the tone control board. We better look at that first. Okay, so flipping this thing over and contorting the probes and everything, I've determined that the bass pots are both in spec. They're both good. The treble pots up here, however, well, they're a little bit different story, and I'll show you what I mean. I have everything set the same between both channels, so we can't really have any discrepancies there. Let me get you where you can see what I'm talking about. And if I go on to the treble pot to the left channel, it's a 50K pot. It's reading 56. It's reading high. And that's even in circuit with things in there. And then the treble pot on the right, if I measure it, $46K, which is more what I think it should be. So there's 10K difference between these two pots. And the funny thing is, it's the right channel that's the bad one. The right channel is the one that actually doesn't read properly. So I'm not sure what to think of that. And I don't know if I can change this little, it really doesn't look like there's much you can do to adjust it, but regardless, it's not correct. All right, so with the exception of this treble pot, and this one's out too, but this one's worse, everything works on here. So if somebody wanted this thing to be perfect, they would need to find a pair of replacement potentiometers for the treble. The bass ones seem to be okay. Everything else works. And what I'm going to do now is, this thing has two outputs. It has a main output that I have going to my bench amplifier, which is a Marantz 2240 right there, and my speakers over there. And the other output is called the auxiliary output, and it's going to this connector right here that I'm going to directly plug into the camera. So you'll hear, without any interference of an amplifier or anything, you'll hear the signal coming from the tape deck through the phase linear 4000 and directly into the camera. So what I'm going to do, because I'm going to have the microphone disconnected, I'll kind of give you some hand symbols, and I'll put some notes up on the screen here when I edit the video. I'm going to first start out flat controls. I'm not going to mess with bass and treble because obviously they don't work right. But we're going to do flat controls, and we're going to start out with just no effect. Just the preamp feeding the signal from the tape deck out to the camera. I'm then going to go over to the peak unlimiter, and I'm going to set the peak limit threshold, and I'll turn this a little bit this way so you can see the lights, till this is just flickering. And I'm going to just use my own hearing to kind of bring things in. and we're going to listen to, once I get this set, I'll flip this up and let you listen to the peak unlimiter downward expander function. Then after that, we'll go to the correlator. I'll turn that on, and I'm going to adjust the correlation level until the highs just start to drop out, because I believe that's how they want you to do it, and then bring it back just a little bit. And then I'll let you listen to what they sound like individually, and then we'll put them all together, and then we'll flip on the active equalizer, which should give you the deep bass. It should actually increase bass, although this thing has a ton of bass to begin with. So let me get that set up. I'll give you a hand signal when we get started, and that's what my plan is. Well, what did you think? I mean, it's kind of hard for me down here to hear everything because I have all this other stuff running in the background. The furnace is on and everything. So critical listening is definitely not going to happen down here. But hopefully, since we have a direct recording into the camera, it should be you should be able to hear it. Now, I will say, if I set the camera record level to be decent, you know, with none of these turned on, as soon as I turn on that peak unlimiter, it was kind of pegging out the camera audio input, and I was afraid you were gonna hear some clipping. Even though it's all digital, you might hear some clipping in the recording, so I had to back it down substantially. So it'll be interesting to see how the recording sounds. So that's it for this. Other than needing a treble knob, you know, control, I should say, this thing's ready to go, and I really got to get it off the bench. I just have too much going on. Dave's going to be here in another 2 weeks, so I'm still on a marathon to get some things done. So until next time, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again soon on the next video. And by the way, this is the kind of tape I used. It was a new tape, fresh. I took the wrapper off, and I recorded it from my bench computer, which has a decent audio interface in it, so we'll see.